Now, before I begin, I would like to say a big thank you to Dr. Anna Fan for actually being a part of this video, and of course taking me more in depth into one of my favorite topics, quantum computing. And now, let's get into it. So hello there and welcome to another tutorial. My name is Tanmay Bakshi, and this time we're going to be going over, well, an entirely new series. In fact, the first video in a new series about quantum mechanics, quantum physics, and especially quantum computing. But before we begin, I'd like to introduce you here to Anna, who's actually a part of the IBM Research Lab in Melbourne. So before we begin, would you like to introduce yourself?
Hi, I'm Anna. I'm one of the researchers at IBM Research Australia, and I am looking into quantum computing.
That is absolutely great. And now let's start off with a little bit about what quantum computing is and really what quantum is in the first place. So before we begin, would you like to give us a quick introduction to quantum mechanics? Like, for example, if I'm a beginner who's never heard of quantum physics before, how would you explain quantum to me?
So quantum mechanics is a theory that explains how things interact with each other on a very, very small scale.
Yes.
So it's very very interesting thing is at a very, very small scale, things act very differently than you would expect compared to the real world. For example, if you had a bunch of pool balls, you expect them to hit off each other and rebound, and you can play pool with them. However, a set of quantum pool balls may not act like that. Sometimes they'll go through each other, sometimes they'll hit each other, sometimes they'll just ignore each other.
Exactly. Now that's basically the weird world of quantum mechanics. And so today we're going to be showing you a little bit more into the world of quantum mechanics and quantum physics with a bunch of different experiments, including proving the fact that quantum mechanics, or more specifically entanglement, actually exists using the IBM Q Experience. We'll talk about that in just a moment as well. But before that, let's talk a little bit more about duality. You know, quantum mechanics is absolutely great for something known as duality.
So the start of quantum mechanics really came about in around the 1900s, where they were looking at light. So light was really confusing because in some stages light acted like a particle, like a bunch of photons, little discrete packets of light, but then in other experiments it acted as if it was a wave. So one of the experiments that looked in was the double slit one.
Yes. Let's talk a little bit more about the double slit experiment, actually.
Yeah.
Sure. So now imagine that you've got essentially like a bowl of water, right? And so this is just liquid. And so if you were to put a little board with two slits beside each other in the water, and if you were to throw a pebble in the water just in front of the board in the very middle, and if at the very end you had a little sort of measurement board where the higher of a wave that touches the board, it'll make a brighter line, and if the wave is shorter there, it'll make a dimmer line. And so you can actually see an animation for that on screen right now if you're not completely getting my description. But essentially, you throw in the pebble, and of course that creates a wave that propagates throughout the liquid. Now, when the wave travels through the two slits, what happens is that creates two separate waves out in those slits, and those two waves go ahead and travel and interfere with each other and create this sort of interference pattern on the measurement board on the other side. However, if you were to do something similar with, say, marbles, and so you've got no liquids this time, but you've got this board with two slits in it and a measurement board, which is just a piece of cardboard, and you're throwing marbles at that double slit board randomly. Now, some are hitting this double slit board and just bouncing back. However, some are actually going through the slits. And this time, instead of seeing an interference pattern, you're just seeing two lines on the back piece of cardboard. And so in this case, you can see that we're not seeing an interference pattern. However, with quantum mechanics, it works a lot differently. And so, let's just say that you're throwing electrons one by one from one side to the other to a measurement board where it'll, display where the electrons hit. And of course, it's going through these two slits. Now, you'd expect the electron, this little particle, to act like the marble, and you'd see two individual lines on the measurement board. However, the really interesting part is that you do not see those two lines. You see an interference pattern using the particles. Now, the way this works is really confusing. The particle acts as a wave and a particle at the same time until it was observed by the measurement board.
And it actually depends on where that measurement takes place as well. So because if you measure it before the board,
yes,
the electron has actually decided which way it goes in, and then you don't actually see an interference pattern if you do the measurement before the two slits, which is crazy.
Exactly. And so that means that if you're sending those electrons even one by one, so you're not sending like a bunch of them and they're interfering with each other, you're only sending them one by one. It exists as a wave of probabilities that go through the slit, that interferes with itself, and that creates the interference pattern when it's measured. But if you were to put some sort of camera or something that actually that interferes and actually observes before it goes through the slits, it doesn't go through both slits at once. It decides which one it goes through and just creates two lines. And there are lots of other, experiments talking about how it's observed, like the quantum eraser experiment and so much more. But we won't talk about that just yet. That'll get a little bit too complicated. If you're interested in that, I might release a new video about those sorts of experiments. You can leave that down in the comments below. But apart from that, let's go ahead and talk about another really interesting concept known as superposition.
Another very interesting thing about quantum mechanics is that while particles can also be waves or particles, they can also have some very interesting properties.
Yes.
So one of the properties of fundamental particles is spin. An interesting thing about spin is that a particle can either have a spin up or a spin down.
Yes.
And in some situations, it can be in both spin up or spin down, and we won't actually know which one it's in until we make a measurement.
Yes.
And this has some very interesting thought experiments around this.
Yes, yes. And so now let's talk a little bit more about the Schrodinger's cat experiment, or thought experiment. And so essentially the Schrodinger's cat experiment basically is an experiment to see how, I guess you could say, these quantum particles actually affect us in our, bigger world where regular physics, Newtonian physics, actually goes ahead and works out. So essentially this experiment is that we've got a box and we've got a cat inside of the box. And we've also got a radioactive particle with some sort of, with some random decay. Okay, and so if this particle decays, a poisonous gas is released, which kills the cat within the box, and there's no way of knowing if this happens from the outside. And so, in theory, and so this is where the superposition comes in, that's a quantum particle, and so it can exist in the state of decayed and not decayed at the exact same time until it's observed. It exists in that sort of 50-50 state.
And then the poor cat that's also in the box is in a 50-50 state of maybe being alive or maybe being dead from the gas from the particle.
Exactly. And so, until we look inside of the box somehow and observe what's actually happening within the box, we'll never be sure whether the cat is dead or alive. It could be in both states at the same time, in theory, just in separate. Now, I won't go into the actual interpretation of the many worlds interpretation. The cat's consciousness goes down a different line. But anyway, we won't get into that right now. But again, if you request for that in the comments, we will create a separate video about that as well. However, for now though, as you mentioned, spin is another very interesting aspect of these sorts of fundamental sort of quantum particles. But there's also, apart from spin and superposition, there's also a really other interesting aspect of these sorts of quantum particles and how that actually ties in with quantum computing. So tell us a little bit more about entanglement and how quantum particles can be entangled.
Yeah, so there's, as well as particles you can put a particular particle in a superposition, what you can also do is set up a quantum mechanical system whereby two quantum mechanical particles can be entangled with each other.
Yes.
So this means that when you look at one, or you measure it, or you compute with it, or you do some sort of experiment with it, you're going to affect the other one.
Yeah.
And this actually doesn't matter how far away they are apart or how close they are. So once they're entangled, they're always going to be entangled quantum mechanically. So which means that if one is spin up, the other one might always be spin up. Or if one is spin down, the other one is always spin down. And you can do some very interesting computation with that. And this actually caused another type of paradox, similar to Schrodinger's cat, around a communication issue. So if you have you set up a quantum system of two particles, and you send them super, super far apart.
Yes.
And then someone makes a measurement one, you instantly know what was in the other one.
Yeah.
So this was the question of, can you actually have faster than light communication between two different particles?
Yes, yes. So tell us a little bit more about that.
Yeah, that was actually called the Einstein something paradox. I can't remember the something. I'll have to look that up later. And you can actually do an experiment to test whether the particles are entangled or they actually have a they're exchanging hidden information behind. Whether they've decided beforehand that we're both going to be spin up or we're both going to be spin down, or whether it's going to be probabilistic.
And so Einstein called this spooky action at a distance.
Oh, there we go.
Yes. Okay. So now though, let's go a little bit deeper into how you can actually use this sort of entanglement superposition with quantum computing. So now let's get into how you can actually use IBM's Q. But before we get into the actual quantum experiment itself, let's talk a little bit more of how you can actually use the supercomputers, these quantum computers themselves. So now let's talk a little bit about quantum computers themselves first. How do they work? What exactly are they?
Okay, so quantum computers are computers that use qubits to compute rather than bits. So the interesting thing about qubits is quantum bits, sorry. Quantum bits is that you can put them in superpositions and then you can entangle them. They work by the laws of quantum mechanics rather than Newtonian physics, which is how all of our laptops today work. And it's really interesting because we think we can compute very, very different things on quantum computers than we can on classical computers. It's all a really new, exciting era of computing.
Yes, yes. And so tell us a little bit more about how these things actually work. Like, what are they? How exactly do these processors work? What do they look like? How do you communicate with quantum bits exactly?
Sure. So we can make quantum bits in many different ways.
Yes.
So one of the easiest way to do it, because atoms or particles themselves have spin and we try to interact with those spins, that is one way to do it. However, it's very hard to get down to a particle level and move them around, and people actually do that today using lasers.
Okay.
At IBM, we actually use superconducting circuits to act as our qubits.
Okay.
So in these little circuits, if the current is going one direction, that means it's in the ground state, or spin up or spin down, for example. Or if the current's going the other direction, that means it's spin up. And the problem with the superconducting qubits is that you have to have them at very, very low temperatures. So they're actually at a couple of millikelvin.
Okay. So how cold is that exactly? Put that into perspective.
That is a lot colder than, for example, outer space. Outer space is at about approximately 2.7 Kelvin. We're at sort of 25-ish millikelvin.
Okay, so as you can see, actually quite much colder than outer space. And so now though, how exactly do you program this? We all know that sort of at the very bare level, we're programming computers using assembler. So what exactly are we using for quantum computers?
So that is actually a new interesting area of research, right? So we program computers using first logic gates, and then assembler, and then your higher level languages. So in the quantum computing world, you program your qubits using quantum gates, and on top of that, we're starting to build quantum assembly languages. IBM's one is called OpenQuasm, and in the future, we want to figure out how to write those higher level languages to go on top of that, like C or Fortran or Python or Java these days. But at the moment, we can also use Python to write OpenQuasm to then access our quantum computer.
Yes, that is really interesting. But now though, let's get into how you can actually use this quantum computing with the IBM Q Experience. So let's get over to that now. Now the computer that's going to power this experiment is actually owned by IBM in their Yorktown Research Lab.
Yes, so in our Yorktown Research Lab, in a fridge that's at almost colder than outer space, we have a 5-qubit machine as well as a 16-qubit machine, which is free for everybody to use on what is called the IBM Quantum Experience. And so that's what I'll be showing you here today.
Yeah, so the Quantum Experience actually allows you to program in OpenQuasm as well as this great graphical user interface that allows you to actually program these quantum bits. The quantum computers that are powering it to actually create different quantum applications. In fact, it has lots of different features like simulating a quantum run and actually running it on a quantum computer. So before you actually go ahead and run your own results, you might want to simulate it, because the simulation just gives you cleaner results because you've got no error. It's very, very
You also
precise.
don't have to wait, because at the moment we've only got one 5-bit machine and one 16-qubit machine, so if you ever want to run something, you have to go join the queue.
Yeah.
And you don't ever know how long that queue is going to be.
Exactly, exactly. However, now though, let's get over to the screen recording. We'll show you how you can actually use the Q Experience.
Okay, so this is the quantum experience. This is how you can program two different qubits. So these are Q0 and Q1 are our two different qubits.
Yes.
And you can see down here, we can actually show you what our quantum computing chip looks like.
Okay.
And it's currently active, which is great, which means you could run on it if you wanted to.
Exactly.
And you can see the particular errors that we're getting on the qubits themselves, the error, the readout, the qubit error, as well as the current temperature of the fridge. So we're actually at 15 millikelvin.
Okay.
So I was a little high before when I said 25. So this particular experiment that I've got running here, or showing you here, is so here we've got two qubits and with time going along the x-axis there. And this is called the composer. And what we do is over time you put qubit gates onto the qubits and then a measurement at the end.
Yes, and I actually also just converted that, just to put that into more perspective for everyone. That's around negative 273 degrees Celsius. And so, as you can tell, very, very cold.
Yeah, sorry about that. I forgot that nobody would know what a Kelvin is.
All right.
Okay, so this is actually one of a 4-part experiment that you do to try and prove that quantum mechanics is actually what causes entanglement, and not perhaps a hidden theory or hidden information behind two entangled particles. Because when quantum mechanics first came out, people, given the spooky action in the distance, were all thinking, well, maybe the particles exchanged information beforehand, then they went to two different places, and then you're just measuring the information that was already there.
Yes.
But they came up with an experiment to try and test whether there was actually information shared beforehand, or whether it was entangled particles.
Yes.
And the way you do this is you set up an entangled state, and then you do 4 different sets of measurements on these different entangled states. So this is one of the sets of measurements. But of course you don't want to have to drag and drop and check and look at all the graphs to compare for each of the 4 different states.
Yes.
So that's why we've created we've got an they call it a Qiskit SDK. So you can program the quantum experience or the quantum computer using Python.
Okay.
So let's flip over to that.
Okay.
So here, this experiment is called the CHCS inequality, named after the 4 people who came up with it. And so the idea is you set up these states and you measure them, and if quantum mechanics is actually a theory and the qubits are entangled, we should see some of this inequality being above 0.
Okay.
And this was actually some very interesting research, and a couple of papers were actually written about this earlier this century, like 2009.
Okay.
And it's actually pretty amazing that these days you can just take the code and run it and get the same graph that it would have taken a team of people, a couple of PhDs probably, to do. And that was only like 8 or so years ago.
Okay.
So this is actually what Quasm looks like. So very assembler-like.
Yeah.
So it's quite nice that we can program the Python to make the assembler that actually runs onto the quantum computer.
I see.
So here are the results I've done earlier, because I don't want to have to wait during the video. And you can see here in this graph, the red line there is the theory, and the blue dots are what we get from the experiment, and the 2 blue lines are where plus and minus 2 are.
Okay.
So you can see that some of the dots are actually above and below 2, which proves that the theory is not a hidden information experiment. So it probably is entanglement.
That is absolutely great. So is there anything else you'd like to share about the Q Experience that IBM provides?
So online, so if you don't think that tanmay is giving you enough information, there's also a lot of tutorials and information about how to use the quantum experience and some of the quantum mechanics behind it for both people who know linear algebra as well as people without any physics background at all, if you want to go program it yourself.
Sounds good. Okay, so then that wraps up this video, and of course there are many more to come in this series. So thank you very much everybody for joining in. That's going to be all for this video. Really do hope you enjoyed or you were able to learn something from this. Of course though, if you do have any more questions, please do leave them down in the comment section below. You can email them to me at taggymanny@gmail.com or tweet them to me at taggymanny. And if you have any questions for Anna, where can people contact you?
So I'm on Twitter at Dr. Annafan. Or, yeah, I think that's
perfect. Yes. I'll put your contact in the description as well, so you can actually go ahead and reach out to her if you've got any more questions for her as well. And that's going to be all for this video. Of course, though, if you do like my content and you want to see more of it, please do consider subscribing to the channel as well, as it really does help out a lot. So thank you very much, everybody, for joining in. That's going to be all. Goodbye.